Hi everyone, and welcome to this short presentation of the work entitled Biomedical Spanish Language Models for Entity Recognition and Linking at BioASQ DisTEMIST. I am Marco Postiglione, and this is a joint work with Vincenzo Moscato and Giancarlo Spervi, all from the PICUSlab research group at the University of Naples Federico II. We participated to the DisTEMIST track of the BioASQ 2022 challenge. DisTEMIST stands for Disease Text Mining Shared Task and is promoted by the Spanish Plan for the Advancement of Language Technology and organized by the Barcelona Supercomputing Center in collaboration with BioASQ. It is focused on the recognition and indexing of diseases in medical Spanish clinical notes by posing two subtracks on named entity recognition, which consists in the automatic detection and indexing of textual evidence of diseases, and entity linking, which consists in indexing medical documents with controlled terminologies. First of all, let's see the methodological workflow behind our submission to the challenge. The inputs to our system are the DisTEMIST corpus and a gazetteer provided by challenge organizers, which contains main terms and synonyms from the relevant branches of SNOMED-CT for the grounding of disease mentions. A transformer backbone network pre-trained with Spanish biomedical corpora has been used for both named entity recognition and linking tasks. In the former case, it has been used to compute token embeddings for a downstream classification head with a linear layer and a softmax activation function. In the latter, it computes concept embeddings for each concept in the gazetteer, which will then be used to link an entity mention to its nearest concept based on a measure of similarity. Let's delve now into the details of the various modules. We use a publicly available pre-trained biomedical transformer backbone, which is based on a Roberta-based model with 12 self-attention layers and masked language modeling as the pre-training objective. The pre-training dataset consists in a clinical corpus containing text data from clinical documents such as discharge reports and clinical course notes, and a biomedical corpus with data from medical crawlers, PubMed, Scilab, and so on. This backbone is used to extract an embedded representation of each token in an input example. Thereafter, a linear layer projects the transformer-based embedding into the label space with a softmax activation function. We have three labels which indicate whether the token is at the beginning, inside, or outside of an entity mention. Model parameters are then optimized by minimizing cross-entropy. In the formula, KL is the Kalbach-Leiber divergence between the two distributions, the first representing the ground truth and the second being the output of the softmax function. Moving to the entity linking approach, it relies on a concept database component. There is a table representing a concept dictionary. To this end, we use the gazetteer provided by DisTEMIST track organizers. Even though not every concept within a gazetteer appears in our training set, we decided to keep all the concepts due to the unpredictability of concept in the test set. Our linking approach is based on context similarity. We learn an embedded representation for each concept, and when an entity mention is detected by the named entity recognition model, its context is compared to the embedded representations of all the concepts in the concept dictionary to choose the most appropriate one. Concept embeddings are basically obtained with an iterative approach, which first initializes them with the embedding of their name and description from the gazetteer, and then updates them with their context embeddings computed with the transformer backbone each time they occur in the training set. When an unlinked entity mention is encountered, its context embedding is compared with all the concept embeddings stored with cosine similarity. We show now results of our methodology with an internal validation and test sets extracted from the available training corpus and with the official leaderboard. We studied the effects of different hyperparameters on our validation set: learning rate, weight decay, and batch size. Our search for hyperparameters divides into two stages. In the first one, we make them vary in large ranges with the aim to detect a smaller range where we'll then perform a random search. In these two stages, we train the model for 2 epochs in each experiment. Given the best results from the random search, we try to increase the number of training epochs with an early stopping approach with a patience value of 5 epochs, obtaining performance coming close to a 0.8 F1 score on both validation and test sets. With regards to the entity linking subtrack, we experimented our methodology with and without the gazetteer. This is because challenge organizers declared that it contains all the entity mentions in the test set, but its size, with more than 100,000 concepts, is much higher with respect to the size of our training data, which contains only 2,000 concepts. When a concept does not appear in the training set, its embedding is determined by its name and description, which could result in many noisy concepts leading to wrong linking results. Since we obtained equivalent results in our experiment, we decided to keep the gazetteer for our submission. Finally, we can see here leaderboard results, which show that our named entity recognition model is by a wide margin the best submission in the challenge, while we cannot say this for the entity linking submission. We observed a big discrepancy between results on our internal test set and the leaderboard, which may be caused by 2 main factors. The first one includes pipeline errors of named entity recognition and linking predictions, while the second regards the inappropriateness of our methodology to be applied with a so small training set. All the concepts which did not occur in the training set are represented by the embedding of their name and inscription from the gazetteer, which may be useless or even detrimental for similarity computation. Further investigation to handle the mentioned problems are thus needed to improve performance. Thank you so much for your attention. If you have questions, you can reach me by email. Bye.